Applications of mass spectrometry. Elucidation of amino acid sequence of oligopeptide, and this protein inhibitor of this is a protein inhibitor of mitochondrial ATPase activity. The separation and MS analysis of peptides are arising from protein enzymatic digestion. The FAB ionization mechanism is shown in the diagram, in which analyte or matrix spot, which is shown over there in green, that is the spot on which the sample is coated, and at the back of the analyte or matrix spot there is probe tip. On the matrix spot, a fast particle beam, that is a high energy electron, bombards, which removes an electron from the neuter molecule, and that creates a molecular ion or a parent ion, and which undergoes fragmentation to form desorbed secondary ions, cations, and they are all called as analyte ions, matrix ions, and they move through the desorbed secondary ion beam towards the extraction grid and through focusing lens towards the mass spectrometer, that is analyzer, where they are analyzed depending upon their M/E, mass by charge ratio. Introduction to field desorption. In field desorption method, a multi-tipped emitter made up of tungsten wire with a carbon or silicone whisker crown on its surface, similar to that used in F5 is used. The advantages of this method is it works well for small organic molecules, low molecular weight polymers, and petrochemical fractions. The main disadvantages are it is sensitive to alkali metal contamination, and the sample must be soluble in a solvent. It is not suitable for thermally unstable and non-volatile sample. The structural information is not obtained as very little fragmentation occurs. Construction and working of field desorption. The electrode is mounted on a probe that can be removed from the sample compartment and coated with the solution of the sample. The sample solution is deposited on the tip of the emitter whisker, either by dipping the emitter into the analyte solution or using a micro syringe. The probe is then reinserted into the sample compartment, which is similar to CI or EI. Then the sample is ionized by applying a high voltage to the emitter. In some cases, it is necessary to heat the emitter by passing a current through the wire to evaporate the sample. The ionization takes place by quantum mechanical tunneling mechanism, which involves transfer of ions from the sample molecule to the anode. This results in formation of positive ions, which are radical ions, and cations attached species such as M plus, Na plus. And these ions are produced during desorption by attachment of trace alkali metal ions present in the unlight. This is a schematic diagram of a field desorption ionization source, in which we have a ion transport capillary and a high pressure vessel and insulation around the vessel, and the FD emitter, field desorption emitter is there, and compressed air and DC supply. Electron impact ionization. It is the most widely used and highly developed method. It is also known as electron bombardment or electron ionization method. Electron impact ionization consists of an ionizing chamber which is maintained at a pressure of 0.005 torr and a temperature of 200 degrees Celsius. Electron gun is located perpendicular to the chamber. Electrons are emitted from a glowing filament, usually tungsten or rhenium. And these electrons are drawn in the ionization chamber through positively charged slits. The number of electrons is controlled by filament temperature and energy. The sample is brought to a temperature high enough to produce molecular vapors. The gaseous neutral molecules are then passed through the molecular leaks and enter the ionization chamber. The gaseous sample and the electrons collide at a right angle in the chamber, and ions are formed by exchange of energy during this collision between electron beam and the sample molecules. The positive ions formed in the chamber are drawn out by a small potential difference, usually 5 electron volt, between the large repeller plate, which is positively charged, and first accelerating plate, which is negatively charged. Strong electrostatic field of 400 to 4000 volt is applied between the first and second accelerating plates, which accelerates the ions according to their masses to their final velocities. The ions emerge from the final accelerating slit as a collimated ribbon of ions. The energy and the velocity of ions are given by the following equation. Advantages of this method are it gives a molecular mass and also the fragmentation pattern of the sample. It is extensive fragmentation, and it's extensive fragmentation and a consequent large number of peaks give structural information. It gives a reproducible mass spectra. It can be used as a GC-MS interface. Disadvantages are also there, which are the sample must be thermally stable and volatile. A small amount of sample is ionized, 1 in 1000 molecules. Unstable molecular ion fragments are formed so readily that are absent from mass spectra. Chemical ionization. In chemical ionization, the ionization of the analyte is achieved by interaction of its molecules with the ions of reagent gas in the chamber or source. Chemical ionization is carried out in an instrument similar to electron impact ion source with some modifications such as addition of a vacuum pump, narrowing of exit slit to mass analyzer to maintain reagent gas pressure, providing a gas inlet, and it involves a two-step process. First step is reagent gas is ionized by electron impact ionization in their source. The primary ions of reagent gas react with the additional gas to produce stabilized reagent ions. Step 2. The reagent ions interact with the sample molecules to form molecular ions. In this technique, the sample is diluted with a large excess of reagent gas. Gases commonly used as reagent are low molecular weight compounds such as methane, tertiary isobutane, ammonia, nitrous oxide, oxygen, and hydrogen, etc. Depending upon the types of ions formed, chemical ionization is categorized as positive chemical ionization and negative chemical ionization. Positive chemical ionization. In this technique, positive ions of the sample are produced. In positive chemical ionization, gases such as methane, ammonia, isobutane, etc. are used. Let's take a case in which ammonia is used as a reagent gas. First, ammonia radical cations are generated by electron impact, and this react with neutral ammonia to form ammonium cation, reactive species of chemical ionization. The NH4 plus ammonium cation, which is formed, reacts with the sample molecule by proton transfer or adduct formation. The equations are shown over there. First equation represents proton transfer and the second one represents adduct formation. When methane gas is used as reagent gas, methane is ionized by electron impact. When methane is bombarded with an electron, it results in formation of a CH4 plus cationic species is formed. Primary ions react with the additional reagent gas molecules to produce stabilized reagent ions. The reagent ions then react with the sample molecules to ionize the sample molecule. CH5 plus MH results to form MH2 plus proton transfer reaction, and the second one is a hydride abstraction, and third one is a charge transfer reaction. That is with the chemical ionization method, that is positive chemical ionization method. In this video, we have seen some applications, how the ionization chamber works, and types of ionization, positive chemical ionization and negative chemical ionization. Elaborately, we have dealt with positive chemical ionization. In the next video, we will discuss or we will continue the other part of mass spectrometry. That is, in the next video we will continue from a negative chemical ionization. Thank you.